Okay, let's get started for today, Tuesday, October 6th. Man, the semester is starting to move right on by. Okay, so I thought I'd throw the schedule up just so we kind of keep an eye on where we are and what's coming up. This is the 6th, right? So this is the last lecture out of chapter 4, and we're in good shape. Just two slides to go over, and then we'll spend the rest of the time looking over solutions to homework problems. And then we go into, we've got 2 lectures on chapter 5, 3 lectures on chapter 6, and then test number 2. So we are on track. You know, I think this schedule is working out pretty well. So right now, unless something changes, we will have test 2 on October 29th. And it will be through iLearn. I have not started making it up yet. I might say it might be a little more challenging than test number 1. Grades were pretty high on test number 1. I trust that's because it was a hard test and you all are excellent students. That's my assumption at this point. But, you know, I might not hesitate to put a little more rigor, as we say, into test number 2. But I mean, I'm not going to make it stupid, but at the same point. Make sure that I just want it to be a good test on the material. So a lot of material. Chapters, 4, 5, and 6, a lot of stuff. You know, first law, open system, second law. So we got a lot to do. Okay, let's see. Let's finish these 2 slides that we have, and then just start working problems. Okay, so I think back when we were doing the mass balance stuff, I actually went over one transient example. And I've got a big transient example using the first law and conservation of mass that we'll go over today here in a few minutes. But so, you know, transient means that what? dmCV dt or dECV dt changes with time. You can't throw away the time-based derivative. That's the way we write it, it's usually on the left-hand side of the equation. So things change, states change with time. So for the mass balance, you know, basically what we do, these equations, we multiply by dt and integrate from the initial time, which is indicated as 0, to the final time, which is t, whatever time we're interested in knowing the answer for. So it's the same equation. You just multiply through all the terms by dt and put the integral sign out front. So, you know, but the biggest thing to remember is that this dmCV dt is not 0. You can't throw it away like we've been doing. And, you know, it kind of changes your thinking. You know, like you're filling up something, you're emptying something, you got more mass coming in than going out, or something like that is going on. And you kind of have to put on your transient hat instead of your steady state hat and just kind of, you know, allow that into the problem for you. Okay. And so when we do that, say on the dmCV dt term, when you multiply by dt, guess what? The dt's cancel, and you've got dmCV. And so when you integrate that from 1 to 2, it's just the mass and the control volume at the end of the problem minus the mass and the control volume at the start of the problem is what, because that's just a differential. And so it's just going to integrate into those 2 terms. So it's pretty, you know, it's not difficult. You just have to be clear. You got to be clear what each one of these terms means. You know, if you're not clear, when you look at these equations, if it's not crystal clear what these terms mean, then you can come back to these wonderful lectures and find it, or God forbid, you could open your textbook and read a little bit of the chapter about that equation and make sure that you're 100% clear. You know, being clear on the terms of the equation and being able to do the units right on the problem is probably 70% of thermodynamics, at least at this level. Okay, so then we get to the right-hand side of the equation. And so that's just going to integrate into the summation of the mass that enters. And see, after we integrate it, these are amounts. They're not rates. So those are amounts. So we're just going to add up during this time period, the summation over the inlets, how much mass came in inlet 1, how much mass came in inlet 2, 3, 4, 5, however many you got, how much came in, and then subtract off the summation of what exited. And again, not a rate, an amount. And here's the definitions. M dot I, amount of mass entering the control volume through inlet I from time 0 to t. ME, M sub E, amount of mass exiting the control volume through exit E between the start and the end of the time that you're interested in the problem, 0 to t. Okay, so let's get on to the energy balance. Well, so it's the same deal. We're going to multiply by dt, and we're going to integrate from 0 to t. And so you see all of the terms up there. And so remember the dot terms, that's a rate of heat transfer, and that's a rate of doing work, just like we just talked through the mass flow rates. And so it's exactly analogous to what we just did. We just got a few different, a few additional terms in there. So the transient term, the integral 0 to t of du cv dt times dt just integrates into the total internal energy of the control volume at t minus the total internal energy of the control volume at 0 when we started the problem. QCV, that's the total, the net heat transfer, minus WCV, the total work affecting the control volume over that time interval, and then the summation. Instead of just masses, now we're going to multiply them by the enthalpies. So the mass at inlet 1, the amount of mass that came in times the enthalpy. And, you know, it's, you know, because we've done that integral, we're kind of assuming that those enthalpies are constant, right? So that the HI and HE have been pulled through the integral sign. Now, if that enthalpy changes with time, then you're going to have to go back and actually do those integrals, and it makes the problem, you know, much more difficult, much more complicated. So what we do in here, you know, you won't have to worry about that. But anyway, so with that, with specific enthalpies at inlets and exits are constant with time, then we integrate into equation 4.25. So I don't know, the rest of it then is just applying these, and we will have a couple of examples of doing that here today. Okay, so let me move on to the examples. I'm going to do a bunch of these, but I don't know. We may run out of gas. I've got some others we can pull up, but so we'll see. And it was brought to my attention that I failed to email out the solutions to assignment 2 out of chapter 4, and I will take care of that right after class today. I apologize for that, you know, just simply a memory lapse. Okay, so we're trying to have an example, of at least one on all of these different types of components. I mean, you certainly have assignments, problems assigned, but I don't have time in class to go over all of these things. But 448 is a pump situation, and I guess this is kind of interesting. I don't know if we have medical aspirations. During cardiac surgery, a heart-lung machine achieves extracorporeal circulation. That means there's a pump pushing the blood through your body. I didn't realize I've read extracorporeal. What in the world is that? But when you read the rest of the problem, you go, oh, that's what that means. So we're going to use a pump operating at steady state. I hope it's steady state. I hope it's not transient. Blood enters a well-insulated pump. So well-insulated tells you what adiabatic tells you you're going to throw out the heat transfer term. You know, that's kind of some of the code words. Rate of 5 liters per minute. Liters is volume. So anytime you get a flow, you should pay a little special attention. Are they giving me volume flow? Or are they giving me mass flow? And of course, you know, volume, we got gallons as volume, liters as volume. You know, we can disguise volume into lots of different units that you may or may not be clear. I mean, you know, some people may not be clear that gallons is volume. You know, I mean, sometimes you just don't think about it. But every time you get a flow rate, you want to think about it. Are they giving me mass flow or volume flow? If they're giving you volume flow, what's the next thing that clicks on in your brain? I'm going to have to find a density or a specific volume, because we typically don't use volume flows in the balance equations, right? It's all mass flow. So see these, you know, it's just all these little switches need to click on in your brain so you can anticipate right there what you're going to have to do. Let's see. Temperature change of the blood is negligible as it flows through the pump. And that's typical. You know, pumps do work on fluid, but compared to the flow rate, the amount of energy that goes into producing heat, it's hard to measure temperature increase across a pump. I mean, it's that small. So that just comes with experience. But if you're working a problem and you want temperature change across a pump, you should expect a small number because it shouldn't be large. Now, an air compressor, you see a gas, that's a whole nother deal. 70–80% of the energy when you're compressing a gas goes into temperature increase and the rest goes into pressure. But because this fluid is almost incompressible, we'll probably assume it's incompressible. It's not quite, but it almost is. Then there's not that opportunity for all that friction between the molecules to build all of that heat inside the gas. Let's see, the pump requires 20 watts. 20 watts ain't much, so it's not a lot. Modeling the blood as an incompressible substance. So incompressible substance, that's code word for what? CP equals CV equals C. There's just one. Negligible kinetic potential energy effects, that's not unusual. You know what that says. Throw out the velocity terms and the elevation terms out of the energy equation. Determine the pressure change in kPa of the blood as it flows through the pump, okay? So steady state, you know, well, there's a picture. It's always good to draw a picture, you know, right? Whatever information you have on it. So steady state, you see it? So he's given this flow rate, cap A, area, V, velocity. So that's meters cubed per second, which liters can be converted into meters cubed per second. What is it? There's 1,000 liters in a cubic meter, I think. When I start giving you metric conversions, you need to be skeptical. Now, if I'm giving you imperial US unit conversions, you can take some of those to the bank. But when I start giving you metric conversions, you better check your conversion sheet. But I happened to look at that this morning, so I'm roughly confident that it's right. Not terribly, though. Well, but so if I've got 5 liters per minute in and I'm steady state, what do I have coming out? I better have 5 liters per minute, you know. Well, now, that's with the assumption of incompressible. If the density or specific volume changed, you know, like with the gas, then that would change. You know, but for steady state, the mass flow would be the same. But once I make the incompressible assumption, then the volume flow is the same because I can't change the volume. You know, I can push as hard as I want to, but I'm not going to change the volume once I make that incompressible assumption, which ain't quite true, but, you know, what the heck. Good enough for government work. Okay, so there's all of his assumptions. I'm not going to read all those to you there in the problem. Okay, so well, here we go. Let's write the first law. So dE CV dt is 0 because we're steady state. Says throw away the heat transfer. So the Q dot term goes away. We definitely have work, right? Because, you know, that's we got a shaft turning, you know, we got a motor, we got a shaft turning somehow. So we got a work term. And then there's only one inlet and one outlet. and the mass flow rate's the same, so he went ahead and factored out the mass flow rate. And so you get, remember we have the NEs minus the outies when we write this equation, so we got the enthalpy in minus enthalpy out, and we're going to, he's including, no, he's not, he's throwing out, that's right. There's the kinetic energy terms, there's the potential energy. So he's throwing all that stuff out, so, you know, pretty quick it boils down to this. And, okay, so we need to evaluate this enthalpy difference. And so if you look for an incompressible substance, you can look back in the chapter, or you can remember it's the integral from T1 to T2, specific heat, not Cp, not Cv, just C of T times dt. But yes, and he kind of missed the slash should be over here on this term. So when he did the solution, they kind of got the slash in the wrong point. But the temperature doesn't change, so dt is 0. So that term's going to drop out. And so it's going to leave the specific volume, which is constant because we're incompressible, because density and specific volume are for with that assumption, times the pressure difference, P2 minus P1. Okay, and so he's going to just make that simplification right here. So this, and notice that over here in the equation, it's H1 minus H2. You know, over here, it's H2 minus H1. So, you know, we've got a sign difference between what we need and what we got. Let me see, has he done that? But did he just put it in there? H2 minus H1. Let's see, so it should be P1 minus P2 over here. Yeah, so he switched the, you know, to take care of the sign, he switched the pressures, P1 minus P2, which would, you know, that's what the minus sign would do. Okay, and then, you know, we know that m dot 1 is m dot 2 is m dot. And if you go back to this little equation to convert a volume flow to a mass flow, this is a cute little substitution trick he does. Whoever works these problems, they're real good at doing algebraic substitutions. You know, they don't start plugging numbers until they get it down to a final equation, which is probably a good idea. It shows good understanding of the equations. So you realize that m dot is the volume flow rate divided by a specific volume. So you multiply this through by specific volume, and you got AV is equal to m dot, A cap V is equal to m dot specific volume. And so he just substitutes that in because he's got m dot specific volume here. So he can just put in cap A, cap V over here, the volume flow rate, because they're equal. And so he's good to go on the equation. And what we want is this pressure change. So we're simply going to bring this to the other side of the equation. That would be a minus, but he switches it to get P2 minus P1, so he incorporates the minus sign in there, and then divides through by AV. So we got minus W dot CV over AV. And then the hardest part of the problem is juggling these stupid units to get everything to work out for you. And realize that the work on the pump is negative because positive work is the fluid doing work on the surroundings. Well, this is the surroundings doing work on the fluid as it goes through the pump. So the outside minus, this minus sign, this first one, just comes from the energy balance. This minus sign we introduced because of the direction that the work, the energy goes into the pump that does work on the fluid. So we got a minus and a minus, that cancels. That, you can get confused over that. And you can certainly get confused. Lord, I'm confused just looking at all those units. But anyway, so here's his liters. There's what, 1,000 liters to a meter cubed. So he's getting rid of the liters. A watt is a joule a second. Yeah, I believe that. And a joule is a Newton meter. Oh, ain't this fun? This is so good. And there's 1,000, a kPa is 1,000 newtons per meter squared. So you get that in there. And then we got to get the minutes out of this into seconds, because we got seconds in the definition up here. I don't know, seconds, whatever. So the minutes and seconds go out, and it wind up with a pressure 240 kPa. So there you go. That's the answer to that one. And he doesn't have any notes on this one. So take a look at that. Like I said, I think I had failed to email these out to you, but I'll get it out to you here right after class. So that's pretty good, basic kind of pump problem. You know, they'll turn it around. They may include heat transfer. You know, just give you different things, but basically you're going to go back to the first law and potentially the conservation of mass, and start throwing out terms and doing your solution based on whatever simplifying assumptions you can make. Okay. So let's take a look at this one. Ah, yes, a little refrigerant. And you know, we want to be sure that we continue to work in the tables. We have steam tables, we have refrigerant tables, we have ammonia tables. I don't know, whatever tables are back there. They all work the same way in terms of the saturation dome and all that sort of thing. You know, you draw the same pictures, the same isobars, the same isotherms, all that. We simply go to a different table to get the numbers, you know, and they jump all over the place depending on what the substance is. 134A with a mass flow rate of 2.3 kilograms a second enters a heat exchanger in a refrigeration system operating at steady state. So okay, we got a flow rate, and it is a mass flow rate, kilograms a second. That's good. Steady state is, so we're coming in at saturated liquid at minus 18 degrees C, pretty chilly, and exits at minus 6 degrees C at a pressure of 1.4 bar. Okay, so this is basically like a cooling coil, you know, and then we're going to put some air on the other side of this and cool it down. A separate heat stream passes in counterflow to the refrigerant, 134A, entering at 50 degrees C. What is that? That's pretty warm. What, 50? That's pretty warm. 50, what is it, times 1.8? What is that, about 80? That's about 100 and 110 in real units, Fahrenheit. I'm sorry, I'm sure I keep insulting somebody, but you know, whatever. And exiting at 25 degrees C. So we're going to cool it down 25 degrees C. So we're going to cool it down like 40 degrees. This is not typical air conditioning stuff. Well, it's probably just a trumped up example for the thermo book, really, but whatever. The other thing that would happen that's not in here, if there was moisture in this stream, it would be condensing out, and there would be a little puddle of water coming out the bottom of this heat exchanger. And he doesn't put that in the problem either. We do that later. The outside of the heat exchanger is well insulated, neglect kinetic potential energy effects, and modeling air as an ideal gas with constant CP, 1.05 kilojoules per kilogram per K. Determine the mass flow rate of air in kilograms per second. Okay, so there's our picture. I mean, we just went through all of that and kind of stated the model. So, all right, so let's take a look at, as he goes through the analysis. Let's see, M.1, M.2, that's on the refrigerant side, and M.3, M.4, that's on the air side. So these first two statements, he's just making sure that we realize that. And then we can write the energy rate balance. So dE CVDT, 0, steady state. And see, now it's interesting. There is heat transfer between these streams, right? But look at where the control volume is. See, the control volume is around the whole kit and caboodle. So what that says is that there's no heat transfer between any part of this device and the surroundings. You know, it would be possible, perhaps, depending on the amount of information that you have and what's given, to make just the 134A a control volume. If you made just 134A a control volume, then you would have a heat transfer term because you've got heat, because you're cooling down the air. So the air, energy from the air is coming across this metal divide that divides the two fluids, and that would be a heat transfer term. So depending on how you draw the control volume determines whether or not, in this case, you have a heat transfer term. So if you put it around the whole kit and caboodle like you did here, then we just say, well, we've insulated all around the heat exchanger, so we essentially have no effective heat transfer to the surroundings. So that's that. There's no work. This stuff is just flowing through here. The only work is flow work, and that's been stripped off and it's part of the enthalpy term. So there's no shafts or no electric wires or anything coming through the walls or anything like that. So the work term's out. And so what do we get? We get summation over the inlets, and we're throwing out kinetic potential energy. So it's just m dot n times the enthalpy. You know, all of those, you know, a term like that for the inlets, and then another term subtracted off for the exits. Okay. And so when you plug everything in, so we can go back up here. So, you know, we've got the refrigerant up here and the air down here coming out. So we've got the zero. Everything's zeroed out to here. So we got the mass flow rate of 134A, which is the same in and out. So it's just H1 minus H2 over here. And the same thing for the air, mass flow rate of air times H3 where it comes in minus H4 where it goes out. Okay? Pretty simple, really. And then so what's asked in the problem is to solve for m dot air. So, you know, what are we going to do? We're going to bring this term to the other side, and notice we're going to switch. Instead of H1 minus H2, it's H2 minus H1. That's the minus sign that he got when it came on this side of the equation. And then we're going to divide through by H3 minus H4. So that's about it. Then it's just looking at properties. You know, if we, so what we would go, well, let's, I don't know how much we need to, we'll do it on this one. Let's go, I want this second ball. And this is SI. So these are your tables. And what is this? 134A. 134A is down here. They're right here. If I can find them. Compress, that's still water. Oops. Water, R22. R22. 134A. Okay, so now, let's see. This is the second problem, isn't it? So what do we want? We want minus 18C, and we want, so that's liquid, minus 18C, and I think that's an enthalpy. So it looks like, what, 26.77 would be saturated liquid, vapor 236. And remember this HFG term, you know, they don't give that on internal energy because you use enthalpy more than internal energy, really. And so they do the subtraction for you. That's HFG. That's just this number minus this number. Because a lot of times, if you're going across the dome, you have to do that. It just saves you some time. Look it up. But anyway, we're looking for this one. I think it's 2677. Yeah, 2677. Okay, so we had to interpolate, I guess, for this second state. So what, we're superheated, he's telling us. So let's see, we're -6 and 1.4 bar. So minus, let's see, he doesn't even have -6 in the table. But you can see -6, see, this is the saturation pressure. So -6, this -6 is halfway in between here. So you see that saturation pressure is going to be, what, 2.3, 2.4, something like that. And we're at, what, 1.4? So we're at much less pressure. So we got to be superheated. Okay. So we're out here. Or you can come to, what, here's 1.4 bar. And say our temperature is what, way greater than that. So we're superheated. What was that temperature again? I swear I can't remember anything these days. -6, 1.4. Okay, so anyway, so here's our superheat tables. There's 1 bar, 1.4 bar, and of course, yeah. So we're -6, so we're in between here and here. And there's your enthalpy column. So it's not quite halfway. What, you're 60% of the way from this number, well, from 0 going this way, or 40% going from here to here. So you got to do an interpolation. So I don't know, eyeball interpolation, I don't know, what, 247, 246. 246 and change. Eyeball interpolation. See how we did. 246 and change. Not bad. Not bad. Okay, so, but I just want to make sure you know where the numbers come from. Okay. Now on the air side, we got an ideal gas with constant specific heat, CP. So this enthalpy difference is just CP delta T. There you go. And so just plugging all this stuff in and pray that the units work. And so we get the mass flow rate of air is 19.28 kilograms a second. Okay? Not too bad. That's pretty good. Okay, let's have some real fun now. That's, let's go on to 88. This is the last problem in the chapter, so what, you got to have some toward the end to kind of test your skills. This is a pretty good problem. This one's, we'll see what time we're starting. It's 10:03. We'll see how long it takes to get through this one. Oh, I know, announcement. Everybody wake up. If you're in the bathroom, come running back at home, whatever. We got an ASHRAE meeting, a kickoff meeting, the 15th. The Thursday after we come back from break. And there's a fellow coming from Nashville, Mark Umbrehagen or something. I never could pronounce his last name. He's going to speak. We'll be in 236, 237, or I'll send out a link to everybody as well. But if you show up, they will pay for your membership. The Nashville branch of ASHRAE, all you have to do, we'll have some applications there, or I guess you could email it in to me and we'll get your name on the list. But you need to get an application into us that day. Mark takes them back to Nashville. They cut a check and send them all to Atlanta, and you can be an ASHRAE. Now, ASHRAE is the Professional Society for Heating, Ventilation, and Air Conditioning, and it's really quite a good society. Now, you may, at this point in your careers, you don't know where you're going to work. There's lots of firms in Nashville. There's lots of jobs related to HVAC industry. There's design, there's contractors that build it, there's test and balancing, there's commissioning, there's marks in technical sales. And, you know, engineers sometimes roll their nose at the idea of selling, but I can tell you a couple of years ago, out of the train office in Nashville, the lowest paid person made $300,000. You go, well, that's not really technical work, but really it is technical work, because you have to get, if you're doing technical sales, you get plans and all that, and you have to actually select the equipment that gets put in the building based on the design of the engineer and the specifications. So you have to work with the engineers, you have to work with the contractors, you have to work with everybody. At the end of the day, if you sell a big job, you get commission. They had one guy who teams with his wife that made a record like $850,000 a couple years back. Because see, he's selling HVAC stuff in Nashville, and the market in Nashville is exploding. So yeah, that's right. I mean, you may say, well, I'm an engineer, I don't want to do that. And that's fine, you don't have to. You can sit at a design firm and work for your 80 to 120K a year and sit there and draw plan, you know, design buildings all day long. And there's nothing wrong with that. Somebody's got to do it. But don't necessarily not look at the technical sales positions as well. Because in my experience, you know, a lot of engineers, especially young folks, they go, well, I don't want to be a salesman. Why would I want to be a salesman? Well, you know, I can think of at least one good reason why I might want to be a salesman. You know, that's a little bit more than my tech salary. I know that may come as a shock to some of you, but it's a little more than I make in probably, you know, 8 or 9 years in 1 year. So anyway, but please put that on your calendar. I will send out a Zoom link, but we'll be in 236, 237 on the 15th of October at 11 to probably 11:45 or 11:50, something like that. Okay, I meant to do that to start a class, and like everything else these days, I forgot. Okay, so let's go on to this. Okay, so I took 4 minutes in the ASHRAE tirade. All right, so it's 10:07. The procedure to inflate a hot air balloon, was kind of weird. I never really thought about inflating hot air balloons. Requires a fan to move an initial amount of air into the balloon envelope, followed by heat transfer from a propane burner to complete the inflation process. So we've got a two-step deal going on here. After the fan operates for 10 minutes with negligible heat transfer with the surroundings, the air in the initially deflated balloon achieves a temperature of 80 degrees Fahrenheit and a volume of 49,100 cubic feet. Next, the propane burner provides heat transfer as air continues to flow into the balloon without use of the fan until the air in the balloon reaches a volume of 65,425 cubic feet and a temperature of 210 Fahrenheit. Air at 77 Fahrenheit and 14.7 atmospheric pressure surrounds the balloon. The net rate of heat transfer is 7 million BTUs per hour, ignoring effects due to kinetic potential energy, modeling air as an ideal gas, and assuming the pressure of the air inside the balloon remains constant, remains the same as that of the surrounding air, determine the power required by the fan in horsepower and the time required for full inflation of the balloon in minutes. Oh, this might be a little problem of a different ilk, as we like to say, you know? I figure I'd give you like 3 or 4 of these on your next test. What do you think? I would not give you this problem on a test. This is like a 4 or 5 page solution. But it is, you know, really, it is a pretty cool problem. I don't know who thought it up, but anyway, that's pretty good. So anyway, so there's process 1 to 2. So there's our balloon laying flat on the ground. I love the illustration too. And so we hook a fan up to the inlet, we start blowing air into it, and it starts inflating. And then after 10 minutes, the volume of this thing is 49,100 cubic feet. It's 80 degrees, and the pressure is 14.7 there. So just assume it's the same as the surrounding. So that's the first part of it. And then we turn off the fan and we turn on the propane burner, and we inject heat into this thing. Is that net of heat transfer? Yeah, I was thinking that as losses, but it's not. That's the amount, that's the rate at which we're adding heat to this thing, 7 million BTUs an hour. And at the end of whatever time interval this is, we have to calculate that for this process. We're at 210 and a final volume of 65,425 cubic feet. So we got 10 minutes up here on this process, but we don't know this, and we don't know the fan work here. So we're supposed to solve for that. Okay, so we go back and reference the assumptions as we go through it. But so analysis. So this is obviously transient, right? This ain't just sitting there in steady state. We got a balloon on the ground that winds up full of hot air, I guess, ready to jump in and take your ride with your bottle of wine and your slice of cheese and your boyfriend or girlfriend, right? And you know, you got float over Sonoma Valley, California, except for the fires, and you know, you can have a good time, right? All right, sounds like fun to me. Okay, so you know, the statement of conservation of mass, or mass rate balance, whatever you want to call it, for process 1 to 2. So we've got dmCV dt, and there is a rate of change of mass in the control volume for sure, and it's just what comes in because we only have one inlet, we don't have any exit, so that's pretty simple. And then we write the energy equation for non-steady state. So here we've got the duCV dt, the change in internal energy of the control volume as a function of time, is equal to the rate of heat transfer minus the rate of doing work plus the mass flow in times the enthalpy in. So, you know, you should be, from the assumptions, you should be pretty good on writing those two. You know, we've been doing a bunch of that. You just have to leave the transient term in it. Okay, well, so first thing he does, he notices he's got an expression for m dot I, and so he's going to take this derivative term and insert it for m dot I. Okay. Let's see, so we do that, and so we get this expression, duCV dt, and there's no heat transfer also for this first process. So we throw away the heat transfer term, and then we substitute it in the derivative term, and so we got dmCV dt times the enthalpy coming in, okay? Well, by assumption 4, the specific enthalpy is constant at the inlet. What's coming in is constant, and so we can look up and see what the state of air entering the balloon remains constant and equivalent to the state of the surrounding air. So we know, so that enthalpy is constant coming in. Okay, so you know, you can integrate this. If you multiply by dt and do the integrals, well, this is just a du, so that integrates into a delta uCV. So this is constant, so this integrates, so you pick up a delta t over here because you multiplied through by dt and integrated it. This is constant, and so that dt integrated into a delta t, and then the h is constant, and so this term, you know, the dt's cancel, and this integrates into just the delta mCV times the constant enthalpy. Okay. So, you know, you might have to get some experience, or, you know, think about that a little bit. But once you get this expression, then, you know, cap U is just the mass times little u. So this is the mass at 2 times the specific internal energy at 2 minus the mass at 1 times specific internal energy at 1. This term we just have left alone. And so this delta mCV is just m, the mass at 2 minus the mass at 1 times the enthalpy. Well, we can simplify because we know we start out, we don't have any mass in it. So M1, M sub 1 is 0. So we get to throw away the M sub 1 terms from here and here. And so it boils down to this. Okay, now when we start thinking about work, we actually have kind of two contributions. Because you got to think, this balloon is expanding. And so that's what PDV work. And we have a fan. And so there's a work term associated with the fan, and there's a work term associated with the expansion of the balloon. And so those two together represent the total work. Okay. And so he's pointing that out here. And so, you know, we've got a W dot in here, but, you know, we're going to, you know, we've done when we multiply it times the DT, then that's going to go away. So if there's not a dot, it's an amount. If there's a dot, it's a rate. Okay. So this is an amount. This is the amount of work for the control volume for the time interval. This is the amount of work that the fan contributes, and this is the amount of the work that the expansion contributes. Okay. So for the expansion, we know we integrate from 1 to 2 PDV. And again, the slash should be over here on the V1 term because this integrates into pressure's constant. We've assumed that. We've made a lot of nice assumptions here to make these integrals much more tractable, right? Which I like. So the P goes through, we integrate the dV, it's V2 minus V1, but V1 is 0, so the V1 term disappears. So this is just the pressure times V2. And then, yes, we have all the fun with the units. So that pressure is 14.7 pounds force per square inch. Remember, when you get the inches, look for the 144 that gets rid of the inches. And so that's what the 144 is there for. This is the volume. And so we got rid of that. We got feet cubed down here. And so then we use the 778 foot-pound force is 1 BTU. And so we convert all of that expansion work, 133,592 BTUs. And that's an amount, not a rate. Okay, so then the work associated with the fan is W dot fan times delta T. So then we're going to substitute all of this into the energy balance. I guess this is the last form of the energy balance right here. And so yeah, so whoops, I get out of there. So the W dot fan times delta T is an amount. This is an amount, this is an amount, and the W is already an amount. So we're okay on amounts versus rates. You got to be careful with that. So we just substitute in this for that work term up there. And so now we can solve for the rate of fan doing work. It's all of this, so, you know, we're just solving, breaking this apart, taking this the other side, this over here, and dividing through by delta T. We should get this. And now we have to figure, I guess, what do we got? We got to figure the mass at 2, which we don't know. We know a volume at 2. And so just the old ideal gas law, P total volume equals to M R temperature. So you apply it at state 2. So we got P2 volume 2 over specific gas constant T2. And again, we got 14.7 pounds force per square inch. We got our 144 to get rid of the inches. Our volume, there's our universal gas constant, molecular weight of dry air. There's our temperature. Don't forget Rankine. Don't be sticking any Fahrenheit in an ideal gas law. And bingo, we come out with 3609 pounds. Well, that's pretty cool. All right, and so Now that we have that, we can go back to this previous equation. We've got the mass. You know, these are just lookups out of the table. We know this, and we know delta T, so we're good to go. These are looked up in the table. I'm going to let you all go verify those just to not run this discussion too long. But you just go to the ideal gas air tables and look them up at the appropriate temperatures. So you should get the enthalpy 128.34 BTUs per pound here. And notice this is an internal energy at 92.04. The units are the same on those. There's your pounds. So we got BTUs, BTUs. And let's see. So we're going to convert to horsepower. And so he's going to use 2545 BTUs per hour. So we got to go from minutes to hours. And there's the conversion to horsepower. And it comes up minus 6.1 horsepower. And it should be minus because what? The fan is doing work on the fluid that's going into. So that looks right. Okay, so that's part A. That was kind of fun. Now, part two, let's see, what do we want to, we want to find the time. So we can go back up here real quick and look at our pictures. So that determined everything for this process 1 to 2. Now we got to go process 2 to 3, where we have the thing with 49,100 cubic feet. And now we're just going to put in 7 million BTUs an hour, and this, you know, and additional air is going to flow in. And it's going to get to 65,425 at 210. And the pressure is the same as the surroundings, and we want to know how long this takes. Okay. Well, guess what? We start out with the same equations. Shouldn't surprise you. So dmCVdT is equal to m dot I. That didn't change. And here is the first law for unsteady state. Now, but we have to put the heat transfer term back in because we're injecting 7 million BTUs an hour into this thing. And now we have the work term. There's no fan, so this is just expansion work, but we have additional expansion that we have to include. And then the mass flow rate entering times that enthalpy entering. Okay, so let's see. We make the same substitution, the dmCVdT for the m dot I term in here. We go through the integration process. Specific enthalpy at the inlet is constant. So we get delta U CV, which then breaks into the mass at 3 times 3 minus the internal energy at 3 minus mass 2, or mass time 2, internal energy at 2. We got the heat transfer term. This integrates into total amount of work. And the m dot CV term is just M3 minus M2 times that constant enthalpy. So that's pretty similar to what we had before. So we want to solve for this delta T here, see? So we do. And so, you see, the only time over on the right-hand side is in the heat transfer term. So that's where the time comes in, because that's BTUs per hour. The rest of these are amounts. Same sort of a thing. We have to solve for the mass and the control volume at state 3. So we're just going to use ideal gas law as before. So mass at 3, pressure 3, volume 3, specific gas constant T at 3. So we know all that stuff. And so we get 3876 pounds. And then we go to the tables. I think we know the temperatures, right? So we can go look up. So the internal energy at 3 is looked up at 114.4 kilojoules per kilogram. Here's our work term. So again, it's constant pressure, so it's just V3 minus V2. There's the difference in volumes. there's the constant pressure, and here's juggling the units. And so we get the work, and the expansion work going from 2 to 3, inflating that balloon further, 44,417 BTUs. And then we can plug in this expression for the delta T right here. And that's what he's doing down here. Mass flow rate, those are the, that's what the internal energy and enthalpy we looked up. I don't know. We'll look and see what all, I forget what all the terms are. Anyway, these are the, yeah, internal energy, enthalpy at 2 and 3, and the work. So putting all that in, dividing by 7 million, and we're going to convert to minutes, 1.04 minutes. And the total time is the 10 minutes for the first process plus the 1.03, so it's 1.04, so 11.04 minutes total. Woo! What do you think? That's fun. So what was that, 7? That's 18 minutes just to talk through. That would take a little while. That would take you a little while. Maybe I just give you one problem on the test. What do you think? One big transient problem. Yeah. I remember when I first took thermo, I just prayed going in that test, please don't give me a transient problem. Please don't give me a transient problem, you know. I mean, once you get used to them, they're not bad, but you know, something like this, I mean, I would think this would take you at least an hour or two to work through. You know, if you didn't have something to look at to guide you through. It would take me an hour at least, I think, to go through all that, juggle all those units and get all that stuff right. So at any rate, I know we're still having fun. Let's see. We got time for another one. Seems like I like 69. I'll tell you, it takes a while to look through all of this stuff. They give a lot of problems in these books. But, you know, I try to select different stuff just, you know, so that you know, be well-rounded in working the problems. Okay, let's see. So here's our picture. Let's just look at a picture. So here's our throttling valve. So we got R134A again, 115 Fahrenheit, 1.5 pounds per second, going through a throttling valve. And we know what? This is our favorite component, right? What's the first law across a throttling valve? H in is equal to H out. I mean, as long as you throw away kinetic potential energy. It's my favorite component. I have to think about the others, but I don't have to think about it. I see a valve with a pressure drop. H in is equal to H out. It ought to just pop up in your brain. Save you time on a test or something. So, not giving us a pressure right here. It's saturated liquid, so we can go look it up, right, in the tables. So we got 115 Fahrenheit saturated liquid. But anyway, it's going to be higher than this, I guarantee you, because that's what that throttling valve does, is drop pressure. Okay, and then we're going to go into a control volume that has a fan, and this is blowing air across a coil. So we got what? 535 Rankine, I don't know, 460, was it 475 Fahrenheit? So that's like room air, return air. And we're dropping it, what is that? 7 times about, we're dropping it about 10 degrees, something like that, across the coil, looks like. A little fan, putting in 0.2 of a horsepower. And we got saturated vapor coming out. So see, that's what happens to that refrigerant. It's mostly liquid coming in, and it boils away. And that boiling process takes the energy for the boiling comes out of the airstream, and so it cools down the airstream. That's what happens inside that coil. That refrigerant is mostly liquid coming in, and it boils, so it's all vapor coming out. So you're just moving across the dome. Yeah, so you assume, usually on these things, you assume there's no pressure drop across the coil, which of course is not quite true, but anyway, it makes it simpler. Okay, so we got three components in air conditioning system. R134A flows through a throttling valve and a heat exchanger, while air flows through a fan and the same heat exchanger. Data for steady state operation are given on the figure. There's no significant heat transfer between any of the components and the surroundings. Kinetic potential energy are gone. Ideal gas for air, constant CP, 0.24. Determine the mass flow rate of air in pounds per second. So there we go. There we go. So I think we're ready just to hop into it. All right, well, so we go back up. So M.3 and M.4 are the refrigerant flows. So 3 and 4, I guess M dot here, and I guess M.5 if you wanted one. But this is all the refrigerant flow through here, the 1.5 pounds per second. Yeah, and yeah, it's all, yeah, 3, 4, 5. And then M.1, M.2 are just the air. Air comes in here, goes out there. Same mass, different volume. Now the volumes will change. Because that air gets colder, it's going to shrink up a little bit in terms of volume flow. Okay, just being clear on that. Steady state form of the energy rate balance for control volume A. So he's going to do the big guy first over here, control volume A. So we got what? We've got an inlet over here. We got an air in, a refrigerant in. We got an air out and a refrigerant out. So that's what you got. So 0 steady state, no heat transfer. All the heat transfer is internal to the system. So we're saying that heat transfer term is always in relation to your control volume, wherever you draw that surface. And so if none of these things are interacting in a heat transfer fashion with that crosses this boundary, then all the Q's internal to the system, and you don't have to account for it. I mean, it is accounted for in the energy balance. Okay, so just making the substitutions with appropriate numbers and mass tags. So we get the negative work of the control volume plus the M dot air times H1 minus H2 plus the M dot refrigerant times H4 minus H5. All that has to equal 0. Specific heat of air, 0.24. So the enthalpy change for the air is Cp delta T. That's pretty simple. So on the air side, we put in Cp delta T. Refrigerant side, we have to go to the tables and look it up. And so we're simply solving this for M.1. So it's pretty simple. Take everything over here and accept this term and then divide by Cp delta T, and you get this, which is pretty simple. See the nth out of state for, oh, okay, so we want to go to the other control volume now, because we got to know H4. Well, so this is where we're doing the energy, we're applying the energy balance at steady state to this control volume over here. So we just got one innie, one outie, no heat transfer, no work. I mean, it's pretty simple. And guess what? It boils down to right here. You throw away kinetic potential energy. You got a 0 over here, so you just divide the M dot, divide the equation through, so it disappears, and you get H3 is equal to H4. So you can write all that stuff up, or you can just look at it and go, I know what that is for that throttling valve. Well, so we've got a pretty easy state to look up at 3. It's the enthalpy of what? Fluid. Is that saturated? It's probably giving us saturated, yeah. Saturated liquid at 110. Easy look up in the tables. So H3, 49.63 BTUs per pound. And please, as you study, go verify these. Verify them enough times so that you're really sure that you can find the right one. Okay. Refrigerant is saturated vapor at 5. State 5 is obtained by H5, so you know the pressure. And so it's saturated vapor at 5, so it's 108.72. Substitute in. Get all your units right. See, we got a horsepower term over here, so we got the 2545 to get rid of the horsepower and give me BTUs per hour. And then we're going to seconds, so then I got to divide by 3,600 seconds per hour to get the hours out of there. There's my mass flow rate, pounds per second, BTUs per pound, 0.24 for specific heat, and delta T. Now notice, if you have a delta T, you can use Fahrenheit. It's probably dangerous to tell you that. You know, if you always use Rankine, it's pretty hard to make a mistake. But, you know, so, I mean, if I'm given Fahrenheit and I'm going to subtract 2 Fahrenheits, if I add 460 to one, I add 460 to the other, I subtract, the 460s go away, and I get the same temperature difference. But like when you go to ideal gas law, you're just plugging in one temperature. Well, it makes a big difference if you're just plugging in one temperature than if you're doing a delta T. So delta T's, you can do Fahrenheit or Rankine, and you'll get the same answer. So it doesn't matter. But like a good thermal book, they're going to show you this in Rankine because they don't want to give you too much rope. They're afraid you'll hang yourself. You know, you go, oh yeah, no, I don't have to do that anymore. That was, you know, that was last semester or something. No, you still do if you're in the ideal gas law. So I don't know. There you go. How are we doing here? 36. Let's take a look at. Yeah, I got one more laid out here. It's pretty quick. Yeah, and I like this problem. Okay, this is what we call a combined heat and power system, CHP, or cogeneration. He uses cogeneration, combined heat and power, same thing, different terms for the same thing. The idea here is that cogeneration, we have one energy source, one boiler, one something that's providing high temperature, high pressure stuff. And we're going to break it into several useful different energy streams. We're going to get some electricity out of this. So maybe this stuff comes in, maybe this is steam, you know, I don't know, whatever it is. And it goes through a turbine turns a generator, and electricity comes out. Or, you know, and then we got some hot water that comes out, we got some saturated vapor that comes out, and we use these things in a manufacturing process. So say we have one input energy and we get several useful energy streams out of it. So that's you can have tri-generation, you can have quad generation, but that's what the concept is. Or they call it combined heat and power, because usually if you're doing this, you have, you know, a boiler or something, and you're putting fuel in that, and then you get steam, you put it through a turbine, you get electricity, so that's the power side of it, and then you get the heat out of the turbine on the exhaust side and use it out in the plant. So you get combined heat and power out of one input. Cogeneration, same thing. All right, so what do we got up here? Let's see, steady state operated cogeneration. So with water vapor, yeah, so we've got high energy steam, basically, 20 bar, 360 C entering location 1. Power is developed in the system at a rate of 2.2. See, we haven't really done all of the stuff on turbines we're going to do, so he's kind of holding off a little bit. We get some bigger problems later where we kind of dig down into the details of the components in all of this. But we get 2.2 megawatts out. Process steam leaves at location 2, and hot water for other process uses leaves at location 3. Evaluate the rate of heat transfer in megawatts between the system and the surroundings. So apparently we have some losses to the surroundings here, and we want to calculate them. And if we need G, it's 9.8 meters per second squared. I'm guessing we do, or he wouldn't have given it to us. Okay, so, and I was looking through here in his solution. You got to read this stuff. It gets confusing if you don't read this. So if you look at these mass flows, he's saying, okay, m dot 1 here, well, that has to equal to m dot 2 plus m dot 3, you know, because we got mass coming in here. It's steady state, so whatever comes in has to go out. So here's m dot 2 and m dot 3. And you notice that what m dot 2 is equal to m dot 3. So then we got that m dot 2 is equal to m dot 3 is equal to m dot 1 divided by 2. And he's going to start substituting these little relations after he writes the first law. Okay. So writing the first law for control volume for steady state, we got a 0, heat transfer term, work term, and we're writing it for, you know, the dotted lines. And so we got what? M dot 1 is coming in, and m dot 2 and 3 are leaving. So this has a plus sign. Inlet is plus, exit is minus, m dot 2. And so he's now including, at this point, he's including the enthalpy, the kinetic energy, and the potential energy for each one of these. And then he's going to make these substitutions. So see, for m dot 2, he's going to put in m dot 1 over 2, which is true. And for m dot 3, he's going to put in m dot 1 over 2. Okay? And then he's going to collect terms. So he's got an m, now everything is times m dot 1. And then he's just going to collect all the enthalpy terms here and call this I. And then all the kinetic energy terms he calls II. And so the 2 goes to 4 because this, when we substitute in, you know, we've got m dot 1 over 2. So all that. And then this is the potential energy terms. Okay. And then he's going to evaluate them. So we're going to go ahead and evaluate all of it. Okay. So looking up the enthalpies, then, you know, H1 minus H2 over 2 minus H3 over 3 is plugging in the numbers. So this bracket enthalpy term turns out to be 1612.82 kilojoules per kilogram. You know, again, verify that you can find the correct data. And then the kinetic energy terms. So we've got, you know, V1 squared over 2 minus V2 squared over 4 minus V3 squared over 4. And all the conversions, say that's meters squared per second squared, and then these are the 2 conversions to get me to kilojoules per kilogram. So that's minus 3.75 kilojoules per kilogram. And then on the potential energy, he's got the someplace he's got a 10 meter. I guess, yeah, this is 10 meters from here to here. Okay. So that gets you, you know, so that just GZ with conversions, that gets you to 0.1 kilojoules per kilogram. So collecting all of the terms, we get the, that's just the heat transfer term that we're going to solve for. This is the work term, and it is positive work because what? It's the control volume shoving that work, that electricity out into the surroundings. So we don't have to introduce another minus sign. This minus sign, again, is from the first law. So then we put a plus 2.2 with this minus sign, and then the mass flow rate times all these terms, and we come up with minus 2.1 megawatts. So, you know, it's all pretty small. What are we doing? We're putting, what is that? Yeah, minus 0.21, and we're putting 2.2 out here. So all these other terms are pretty small, but it's just, what's he saying there? Can't read it. Be patient, it'll go away. There we go. The effects of kinetic potential energy are minor in this application. Well, the heat transfer is more minor than the kinetic energy term, but anyway. Well, no, probably not. That's right. This is kilojoules and this is megajoules. So I guess 1, 2, 3. So that's 210 kilojoules. Yeah. So I guess the heat transfer term is bigger than these two by far. Okay. I think that's probably about enough. I will email those solutions out to you, and we will move into chapter 5. So be looking at the chapter 4 problems. I will send you the PowerPoint because we'll be in chapter 5 on Thursday. So we do keep moving in this course. Keep working. I mean, I think it's all pretty accessible. I think it's all pretty straightforward, but boy, you don't want to let this stuff rest. You get a chapter behind and this stuff will eat you alive. I'm telling you what, it seems easy when you stay up, but it'll eat you alive. And the material slowly gets a little more complex as we go. So don't rest on your laurels. Keep after it. Okay, thanks guys. See you next time.